Hi everybody, hope this video finds you doing well. We are going to be looking at section 4.8. Our learning goal is to be able to use x-intercepts to graph polynomial functions. We want to be able to use the location principle to identify zeros, and we want to be able to find turning points. What's a turning point? Well, right here, the function's going up, down. That's a turning point. It changes directions. And we also want to be able to identify local maxes and mins. So right here we have two turning points. This is also called a local max. The reason it's called a local max is because relative to these points right around it, it's a high point, so it's a local max. We can also call it a relative max. This is called a local minimum. Can also be called a relative minimum. It's a low point compared to those others. So these are not only turning points, but they're also what we call extrema or a max and min. All right. Let's look at some definitions here. If we have a polynomial function and it's written in descending order, see how we've got x to say the fourth, then 4 minus 1 is 3, then we'd have to the second, to the first, the constant. The following statements are equivalent. A zero is going to be, that's something we know about. It's like right here. This would be a 0. This would be a 0. This would be a 0. Those are the places where the function equals 0. X minus k is a factor of the function, of the polynomial. So let's say that that's at, let's say it's at -1. So as a factor, that would have been x plus 1. Let's say this is at 3. So 3 would be the 0, but the factor would have been x minus 3. Whereas that one would have been x plus 1. I hope I said that, not minus. This one would be, let's say that's at 5, then the factor would have been x minus 5. A solution is going to be a root. It's whatever makes the function equal 0, just like a 0 is. And an x-intercept, if we have k as a real number, then k is an x-intercept of the polynomial function, as long as, the function passes through that point of k0. So back here, -1, 0. That's going to be an x-intercept. That's going to be a 0. Right here, 3, 0. 3 is going to be the x-intercept. It's also 0. It's also a solution to this function. All right, all of it goes together. Okay, so in our notes, it says to graph two things. Get out that graphing calculator. Let's check this out. So we're going to go to y equals. I'm supposed to put this one in. X raised to the fourth, arrow out, minus 11x cubed plus 33x squared minus 9x minus 54. Okay, I'm going to graph that one here in a minute, but we're also supposed to graph this one. Let's see what this one is. X minus 3 quantity squared times x plus 1 times x minus 6. Okay, so we're supposed to graph these at the same time. I'm going to do the old zoom 6 to make sure we've got the standard screen. Here comes the first function. It's got to think about it. There it comes, coming back up, going back down. Yeah, W. Okay, now here comes the other one. And, oh, it's in red. There we go. Well, what do you notice? They are the same, aren't they? They are the same. So that means they're actually the same functions. So if they're the same graphs, they're the same functions. Which of these two would be in standard form? This one, okay, f of x. It's going in that descending order, and it's all multiplied out. That's what standard form is. What is the form that g of x is written in? These are equivalent, but this one is written in factored form. The nice thing about factored form is I can quickly see the zeros. I don't even have to go to this. I can see the zeros by looking at this function. Okay, whatever makes it 0. I plug in 0 for g of x. What are the values of x that are going to make it equal 0? Well, the zeros are going to be, let's list them out. Whatever makes that 0, that's 3. That's -1, and that's 6. Now, I would actually say that 3 has a multiplicity of 2. We don't have to jot that down yet, but that's going to be coming soon. It's actually going to be a 0 twice. In fact, I might even want to list it twice. Let's go ahead and do that. Let's list it twice. 3, 3, because it's a factor twice, -1, and 6. Okay? And the reason we do that is because this is saying that we should have 4 solutions, and now we're saying we do. We have 3 positive real solutions and 1 negative real solution. We could look back at that sign change, Descartes' rule of signs. We have 1, 2, 3 sign changes. 1, 2, 3 positive zeros. It's all connected. It's so cool how it all just relates to each other. If f is a polynomial function and a and b are two real numbers such that f of a is less than 0 and f of b is greater than 0, then f has at least one real 0 between a and b. That's a little confusing. What are we talking about here? Well, I want you to look at some numbers. I'm just going to make up some numbers. Let's say we go -2, -1, 0, 1, 2. These are our x's, and these are our f of x's. So let's say it goes -6, 2, 5, -1, -7. Okay? Between which two integers would there be real zeros? Well, look at this. When x is -2, my y value is down here at -6. If x is -1, my y value is here at 2. Aren't we going to have to pass through a 0 to get from here to here? So what this is saying is, when I have a y value that's less than 0, and then I have a y value that's greater than 0, we have to have at least one 0 in between there. So there must be a 0 between x equals -2 and x equals -1. Everybody agree with that? Okay, let's look at the y's now. Positive, so we're at 2, then we go up to 5, then we go to -1. Well, there's going to have to be a 0 there. We have to cross through 0 to go from 5 to -1. So we also have to have a 0 between x equals 0 and x equals 1. Okay, what about if we're at -1 and we go to -7? Would we have to have a 0? No. Okay, so that's what that's saying. We have zeros between these values. All right, now they write it out like this. We can make our own chart. When x is 2, y is -3. When x is 3, y is -1. When x is 4, y is 2. So where would we have zeros? 0 between what? Well, it's not in between -1 and 2. The zeros occur. We have to hit 0 in between x equals 3 and x equals 4. See, the common mistake here is people will say, oh, 0 is between -1 and 2. Well, yeah, of course it is. Everyone knows that. But what are the x's that are causing that 0 to occur? The x's of 3 and 4 are what's causing it. All right, turning points. The graph of every polynomial function of degree n has at most n-1 turning points. If a polynomial function has n distinct real zeros, meaning exactly n real zeros, then its graph has exactly n-1 turning points. Okay? So we just take that degree and we subtract 1. So think about this. What is the most possible turning points for this function? Hopefully you're thinking or saying or telling your parents 4, right? That's going to be the most possible turning points we can have. Write a polynomial function with a maximum of 6 turning points. Well, what's the degree going to have to be? 7, right? So f of x equals 2x to the 7th. I can put anything else after this. I don't have to have a 2 there. I can have any number, but I have to have x to the 7th. I don't know. Just put anything. There we go. That would be one, okay? As long as you have x to the 7th, you don't even have to have anything else. You could just put that. That would have a maximum of 6 turning points. Even an odd function. A function f is even when f of -x is the same as the original function for all x in its domain. The graph of an even function is symmetric about the y-axis. A function f is an odd function when f of -x gives you negative f of x, meaning the exact opposite of the original function, for all x in its domain. The graph of an odd function is symmetric about the origin. One way to recognize a graph that is symmetric about the origin is that it looks the same after a 180-degree rotation about the origin. This is an even function. See how if I have x, I have y, but if I put in -x, I also have y. It's symmetric about the y-axis. Odd functions, I put in x, I get y. I put in -x, I get -y. That's an odd function. If I could rotate this 180 degrees, I get the same exact function again. Okay? Describe whether the function is even, odd, or neither. So what I'm going to do is I'm going to have to replace x with negative x. Everywhere I have an x, I'm putting in a negative x. Nothing else changes. Circle it if you need to. Okay, negative x to the 6th, that's positive times a negative. Negative x squared is positive times 5. And plus 2 doesn't change. So now I look at this f of negative x, and if it's exactly the same as the original, then it's even. Is it exactly the same? Yes. So this is going to be, not yes, whoops, even, right? I want to show you it. I mean, if I have a calculator with me, I can even just graph it and look at it and see if it's even. If it's symmetric about that y-axis, it's even. Let's see what it looks like. Yeah, see how it's symmetric right there. So it's even. Okay? All right, let's look at the next one. Everywhere I have an x, I'm going to have to put in a negative x. Just x there, put in negative x, simplify it. A negative x cubed is negative times a negative is a positive. A negative times a positive is a negative, and the plus 2 doesn't change. Now I look at it. Is it the same? No, so it's not even. Is it exactly the opposite? Negative went positive, positive went negative. Uh-oh, that one didn't change. So to be odd, every single sign has to change. So this one's neither. Okay. Lastly, put in a negative x. Everywhere negative 2 doesn't change, put in a negative x there. 5 doesn't change, put in a negative x. A negative x to the 5th is negative times negative is positive. Negative x cubed is negative times positive is negative. So it's even if it stayed exactly the same. It definitely did not. It's odd if every sign changed. If this whole thing got multiplied by negative 1, that's what happened. I don't know why I put 2, that's 5. All right, so this one is going to be an odd function. Okay? Graph g of x equals this. On the graphing calculator, identify the x-intercepts, the points where the local max and local minimums occur, determine the intervals over which the function is increasing and decreasing, be able to write these in both inequality and interval notation. Great, let's do it. Go to y equals. It goes to the 3rd, yeah. Graph it. Kind of hard to tell where those x-intercepts are. All right, so here's what I'm going to do. I'm going to look at my table, see if I can find one. Ooh, can't. Okay, so I have x-intercepts. In between negative 2 and negative 1, I have an x-intercept because I can see how this is changing. Positive to negative, negative to positive. So I've got several x-intercepts in there that I can't see. So I think they want us to find them exactly. So what I'm going to do is a couple of different things. I can go and put in y equals 0. I want to know where does this function equal 0. So I'm going to do, actually I want to show you something else first though. I'm going to say my x-intercepts occur between x equals negative 2 and x equals negative 1. Then I'm going to find them in exactly too. So also in between negative 1 and 0, just understanding that location principle. And then also right there, oops, sorry you guys can't see that. So see what I did? That went positive to negative. So in between those two x's, right there, and then in between these two x's, and lastly in between these two x's, so in between 1 and 2. And I'm also going to find them exactly. I want to show you that. All right. Go back to y equals, zoom. Oh, no, I don't want to do that. Second, calculate. I want to find my points of intersection now. and I want to find this first x-intercept. I get close to it, and I do enter, enter, enter. Ooh, okay, it's not exact. So I'm going to say my x-intercept is about, we'll round to the nearest hundredth, negative 1.32. There's one of them. That's my point, approximately. Second, calculate intersection again. I'm going to get close to that next x-intercept. And that I'm going to round it to negative 0.430 approximately. And the last one, this is an easy way to find x-intercepts, 1.75. So those are my approximate. I'm just putting approx. There's where they are. Okay, points where the local maximums occur. Okay, here is a local max. Oops, trace. There's a local max right there. It's a high point. Here's how I find that. Second, trace, calculate a maximum. I go to, it says left bound, so I go to that left side, I push enter. Right bound, I have to go to that right side of it, hit enter. And see how these arrows are pointing where it is? If yours aren't pointing in that direction, then you did it wrong. It's going to say guess, you just push enter, and then it's going to tell you where it is. So the point where my maximum is, I'm going to round it again, 0.91, comma, 5.04. There's where my maximum is. Okay, let's circle that. Points where the local, I think I meant this should be minimums. We just did that. Change that to minimums. You can just call it mins. Second, trace, calculate. Now we're going to find the minimum, so we're going to come over here. We have to be on the left side of it, so make sure there's the 0, make sure you're on the left of it, push enter. Arrow over to the right, make sure you're on the right side of it. Excuse me. It'll say guess, and it's asking you, is it in between those two arrows? And we push enter to say yes, and here's where our minimum is. Negative 0.91, comma, negative 1.04. Okay, that's approximately where that minimum is. Okay, intervals over which the function is increasing. Well, the function is increasing from here to here. I just found those points, didn't I? So it's increasing from an x value of negative 0.91 to positive 0.91. Those are the x's that are causing it to increase. Intervals over which the function is decreasing. Well, it's decreasing for all these x's all the way over there. What's that called? It's called negative infinity. So from negative infinity until this point, which we just found, so to negative 0.91, our function is decreasing there. Then our function is decreasing from this point down. We always use x's here to describe it. So the x value right there, we just found that, it was 0.91. So 0.91 to infinity. It's not negative infinity, guys. The x's are going this direction in positive infinity. So any x from 0.91 approximately to infinity causes this function to decrease. Okay? All right, take a little break if you need to. If not, I'm going to finish up. Oh, guess what? We're finished anyway. Yay. Okay, I got it in under 20 minutes. So this is kind of the challenging part right here, guys. Once again, just remember, anytime you're writing an interval, intervals use x's. You always use x values. Oh, wait a minute. Something else that says be able to write these in inequality and interval notation. So the way I would write this in inequality form would be that from negative 0.91 to 0.91, oops, less than. So any x that's in between there Any x that's greater than this but less than this is going to cause the function to increase. And I don't want to say equal to, because at that point it's not increasing or decreasing. Okay, so that's going to be the answer. This is interval notation, this is inequality. All right, and then here, the function is decreasing as long as x is less than, not equal to, because when it's equal to, it's not doing anything, it's not changing. Okay, when x is less than this, or when x is greater than 0.91. So interval notation, inequality notation. Some of you still don't have that down, which is which. Interval uses the parentheses. Inequality uses less than, greater than. Okay? So work on all that. We're going to have a worksheet to do that kind of puts all this together. It's going to be worksheet 4.8. You're going to work on that, just a couple of problems tonight, and then you'll have some more time to finish that. You're just going to do like the first 2 problems. All right, good job. Hope that made sense to everybody. If not, just ask questions.